Next problem. The old inverted cone. Before we really get into it, I just want to really emphasize your teacher loves him some cones. I mean, I really like cones. Now, you need to imagine that I'm banging on the board right now very loudly and screaming about the fact I like inverted cones. I really like these problems right here. This type of problem. I don't know if I'm making this hint enough to you, but I really, really like me some inverted cones. Okay, cool. Let's talk about it. So water is poured into a conical container at the rate of 10 cubic centimeters. Hold on. Let's just start writing stuff down as we go through this. 10 cubic centimeters per second. That's got to be a rate. That has to be the change in the volume with respect to time. It just has to be. Because we have a cubic, and it's changing. That's got to be something that has to do with volume. So we got that part. Now, the cone points directly down. So it's upside down, inverted. Watch Top Gun. It'll tell you all about it. And it has a height of 30 centimeters and a base radius of 10 centimeters. We want to know how fast is the water level rising when the water is 4 centimeters deep, when the height is 4 centimeters. Let's go make a picture. Oh, ta-da! There's already a picture made. Already got our picture. Got it to where the base radius, just saying that the radius of the cone is 10, right down to the bottom. But, oh, it's inverted, so it's upside down, so it's up top instead. All right, so we look, we got our height is 30 centimeters, and then I wrote the H inside and the R so you can see it. All right, so water's going to get poured into it. So let's imagine the water's getting poured in. Let's get that. And we get to, it's up to this height right here. It's just up to that height right there. We got water down inside of there. But what this does is it starts to begin this idea of similar triangles. So we'll start to do it in blue, and we just look at this triangle here. This triangle right in here. And this is going to be the first one where we have to do the substitution step. We're going to need to do this because we're going to end up with a couple of variables here. So I think I'm getting a little ahead of myself. Why don't we write down the formula? Why don't we write down the formula for the volume of the cone? Because if we're just trying to do all of this work and we don't know what the heck we're looking for, we're just lost in the dark. So the volume of a cone, the volume is 1/3 pi r squared h. Now when we're doing these problems, if you're having to do the product rule, you're probably doing it wrong. We want to get everything in terms of one variable. We want a v on one side, and then we just want r's on one side. Or we can have a v on one side, but we need to have h's on the other. And for our game, since we're given a height with the when, we're going to want to get everything in terms of h's. So this is the game for which we're going to have to play. Similar triangles game. We already know our height is 30 and our radius is 10 at the top. But let's start getting rid of these r's here. Let's get rid of that because that's not really r. That's just going to be, that's 10. It's never going to change. Now this h, don't call that thing h. Let's get that the heck out of there. Let's call this just 30 because that's what it's always going to be. It's always going to be 30. But what can change is our radius and our height. These, as we move up, we have the water in it. Those change. Not the 30, not the 10. So let's set up the idea of similar triangles. So we have our little blue triangle here where we got our R and our H. And then let's pull out our purple triangle with our 10 and our 30. Now these ratios have to line up. We can actually set this up and say that, well, the radius over the height, well, that's got to be equal to the radius over the height of the whole triangle. It's similar triangles. This is how trigonometry works. So let's go solve for one. Let's get everything in terms of h's. So let's get rid of those zeros, and we have r over h is equal to, and then when those cancel out, that was just 1/3. So why don't we multiply our h over to the other side and we get r is equal to h times 1/3, or h over 3. Well, neat. Now we can take this thing and we can go pop that in for r. This is our first substitution where we're going to do this before we differentiate. So this is this idea when we deal with cones, we want to think similar triangles. We're going to use this game quite a bit. Be ready for it, because one more time, your teacher loves him some cones. So you want to make sure that you're ready. Now let's see. Once we're here, we're home free. Pretty much everything's going to be solved out for us. We say that the volume is equal to 1/3 pi r squared times h. But we want to get everything in terms of h's. So instead of writing an r, we're going to write what it's equal to. H over 3. Well, now let's do a little bit of algebra. We'll clean this up, and we get 1/3 pi times, that's h squared over 9 times h. So I think our volume is equal to the 3. That's a pi over 27 times h cubed. There we are. Let's go take one of the simplest derivatives we'll do in this whole class. We'll pop it up here. We'll start again. Our volume is equal to our pi over 27 times h cubed. Let's start differentiating. So the derivative on v is equal to the derivative on v with respect to time. On the h, our 3 is going to fall, and that's going to cancel with the 27 a little bit and leave us with pi over 9. And we're going to lose a power on our h, and that's going to become h squared. And don't forget, every time we take a derivative, every single time, the derivative on height with respect to time. Cool. Well, let's see what we have. Well, we've taken a derivative, so we can plug in the when. So that h can be plugged in with our 4. Let's go plug that in. We pop it back over here. Yep, there goes the 4. We got that. Our pi over 9, of course, that's not going to change. That's staying there. Now, what do we have? What are we even solving for? We're solving for how fast is the water level rising. Oh, shoot, we're solving for dH dt. And we already know dV dt. Let's plug it in. dV dt was equal to 10 centimeters cubed per second. And we're looking for dH dt. Well, let's do some algebra so we can solve. So we're going to get, what, 16 pi over 9 once we square that up, dH dt. Let's multiply both sides of this by its reciprocal, and we're going to end up with 90 over 16 pi is equal to dH dt. Now, this is your teacher's pet peeve, so please don't leave this as 90 over 16. Those are both even numbers. Half of 90 is 45. Half of 16 is 8. So I think this is a little bit better of a solution. Is equal to dH dt. However, when we want to write our answer down, we're going to say that this is equal to 45 over 8 pi what? What are our units? What was it even in? It was in centimeters, right? We were in centimeters. So that must be since height is just a length, it would be centimeters per, and what was our units? Was it seconds? Was it feet? Seconds. There it is. And there is our solution.